Bismillahirrahmanirrahim. The topic today is the wavefront, or as it is sometimes called, the frontal method. To date, our approach has been this, and let's call it the standard approach. It has been this. You start with element number 1. You have these element level equations. This is K, U, F, and you have this connectivity table in place, which tells you the relationship between element numbers and the node numbers, or degree of freedom numbers. Now, according to this connectivity table, you have this system matrix in place, this bigger matrix, where all elements are going to be placed at their appropriate places. So using the connectivity table, you bring these values, all the relevant values, and impose them on this system matrix at the relevant place. Also the force vector will also take its relevant place in the system matrix. Now you go on to element number 2. Similarly, you have some values here. Again, using the connectivity table, you bring values to their appropriate places. The force values also take their relevant places in the system equations, and you repeat this process until you reach the last element. At that time, you'll have the complete K system equations values, K system matrix. Then you have the system U vector and the system force vector, and then you apply the boundary conditions, followed by solution. Solution means you calculate all the values u1 till un. This is the standard approach. You have done it so many times. Now this works fine, but there are times when there's a problem here, and those times are when your system size is very large. For a system with n degrees of freedom, this K matrix takes the size n into n, U vector n into 1, and F vector n into 1. Now for smaller or medium sized systems, there is no problem. But if the system size is very large, then you'll have a huge amount of information here. Now this system necessitates your working memory to have all this information at one time, to store all this information at one time. Now this can be a problem with systems with smaller working memories, that is RAM. Now this wavefront method, what it does is, precisely for these problems, it allows you, as opposed to the standard approach, this wavefront, this allows you to do a certain kind of procedure so that you reduce the effort on the part of the working memory, that is RAM, at the cost of utilization of the hard disk, somewhat more utilization of the hard disk. And now it might look like a trade-off between one thing and another thing, but obviously if somebody tells you that there's a system that reduces load on your RAM with slight increase in the requirement, the storage requirement on your hard disk drive, I think you'll take that any day. It's a very good bargain. Hard disk is very cheap. There's no dearth of storage space for you. Now RAM is still expensive, so this is a good approach. Now what we do here is we start essentially in the same way. You start with element 1 and bring it to its relevant position in the system matrix. Similarly, the same goes for force vector. Now element 2, bring it again here, Now, so far there's no change, but let's say at this stage, your connectivity table tells you that the degree of freedom 3 has occurred for the last time, which means that from element 3 onwards up until the last element, there is no reference to degree of freedom number 3. That is, none of the elements after element 2 has degree of freedom 3, which means nothing but u3. So this is the time when you eliminate u3. How we do that? We remove the row as well as the column associated with degree of freedom 3. That is the third column and the third row, which will result in a smaller K matrix and a smaller F matrix, F vector. Now, obviously, we'll move on to element 3 then element 4. But at a certain stage, again, you'll encounter another degree of freedom that has occurred for the last time, and then you will remove that also. So you keep on moving towards the last element. The matrix and the vector size will keep on increasing and decreasing, and as you proceed towards the final elements, then you will see that the reduction becomes more and more, and at the end you will just have 1 degree of freedom in the system. I'll explain that later on, but the conclusion of it all is that at the end you will have just 1 degree of freedom left. That is the last degree of freedom. You will calculate that, and then you will come back, and by back substitution you will calculate all the degrees of freedom, because before eliminating u3, you would have written this information. You cannot just eliminate something from a system, because then you will lose information. You will write this information, whatever you eliminate. Before eliminating, you write that information in your file in storage, that is your hard disk. So at every stage, whatever you eliminate, you keep on writing equations in the hard disk. But the plus side is your system size will never achieve the size that you had here. If this was n into n, this will be a fraction of that. Now here you need some space on hard disk, but you need it anyway. Here you need a large working memory. Here working memory requirement is reduced. So this is, in a nutshell, this is your wavefront method. This is just an introduction. If we move on to more concrete terms, let's explain what this elimination actually looks like. The thought process sounds promising, so let's see if and how we can pull it off in real questions. I'll just start with some symbolic values here, variables, but then very soon I'll start using some real numbers also. K21, K22, K23, K24, K31, K32, K33, K34, 0, K42, K43, K44, and there are some other numbers also. I'm not writing the whole of this matrix. This is just symbolic anyway, so doesn't matter. Let's say after the assembly of element 2, like we just discussed, after the assembly of element 2, this is how your system equation looks like. Now the connectivity table has told us that u3 has occurred for the last time. Now if that is so, then we can eliminate this row and this column. Let's see, can we do that? Of course we can eliminate this, but like discussed earlier, we need to, we don't want this information to be lost, because u3 will have to be calculated eventually. So you have to have this sort of information written in a file. How you do that? k31u1 plus k32u2, I'm just simply writing the third equation, plus k33u3 plus k34u4, plus there could be other values also, I have not written them here, but whatever other values are, is equal to f3. Now if we rewrite it, u3 is f3 minus k31u1 minus k32u2 minus k34u4 minus whatever other values are over k33. This is written in a file. Once this has been written in a file on your storage, your computer storage, then you can just remove this, because eventually at a certain stage you will have to calculate u3, but you will have this equation stored u3 in terms of other degrees of freedom. So you'll just put in those values if these are known, and these will have been known at that time. Then you can simply calculate u3 and then move on. Now this sort of thing makes it now possible for you to remove this, all this. But when you remove this row, then just notice that this column, this row, it's all right to remove this row now, but when you remove this, notice that all these values in this column, k13, k23, k43, all these values are being multiplied by u3. Now you cannot just ignore these values, and if you remove this, this means that this will also be removed, because this is being multiplied by u3, which you are going to remove. So you cannot just simply ignore these values, because actually the first equation reads like this: k11u1 plus k12u2 plus k13u3 etc. is equal to f1. Now k13u3 plays a part in this balance on the left and the right hand side. Similarly, this k23, this k4, these play a part. So you cannot just remove these values unless these values are 0, because 0 multiplied with something doesn't matter. So how to make these 0? You have to make these. How to do that? We will factorize this equation and then subtract or add to other equations and make sure that these become 0. In other words, we'll utilize row operation. We'll make sure all these column values become 0, so that we have no problem in eliminating this column as well as this row. And when that happens, then you know that you cannot apply row operations on just this column only. If you are going to apply row operations to make this column value 0, then you have to apply the same row operation on all other elements, including the force terms. So your values then will become k11 prime, that is, some sort of operation has taken place. So this k11 might not necessarily be equal to k11 prime, it might be different. It will be different in many cases. k12 prime. And if that is done, then you have this 0, and this was also 0. Similarly, k21 prime, k22 prime, again 0, k24 prime. k31 prime. You don't need to prime here. This is simply k33, k34 0, k42 prime, k4 this is again 0, we are making this 0, k44 prime, and so on. There will be some other values also, u1, u2, u3, u4, similarly f1, f2, all these will be 0. Whatever values, if they are non-zero values being multiplied by u3, you have to make them zeros, which will cause these values to become something with a prime on them. Now at this stage there's no difficulty in removing this and removing this, because this again all zeros multiplying with something doesn't matter. These are values, yes, but u3 you already have all this information here. So now you remove this and you remove this, and what you get is k11, k12 prime 0, k21 prime, k22 prime, k24 prime 0, k42 prime, k44 prime. There will be some other values. I'm just writing some values to illustrate my point. Now u1, u2, u4 now. So you have now 1 degree of freedom less in your system. f4, f3 is gone now, u3 is gone now. So what is happening actually is system size after one element, then two element, it became a certain size, then it reduced because you were able to eliminate 1 degree of freedom. Then you move on, there'll be another increase, maybe another increase, but then pretty soon you'll have another degree of freedom that will have occurred for the last time, then you can take that away. Now this is a degree of freedom that was unspecified, that is you didn't know the value of u3, you just knew it occurred for the last time. What happens with a specified degree of freedom, that is boundary condition? Of course these values are with prime here, because whatever row operations you perform, you have to perform across the board, so these will also be changed, and here these as well. So what happens if we return to the thread, what happens to the boundary conditions that are specified? Recall that in your ordinary approach, boundary conditions are handled at the very end. The known displacements, they are handled at the very end after completing the whole K matrix. Here, that will defeat the whole purpose. We are here trying to get rid of all degrees of freedom as soon as they occur for the last time. Now, one of those could be a degree of freedom with a boundary condition on it. That is, in that case, some degree of freedom will occur for the last time, but you know its value. For example, u2, that is its value is a2. A2 means it could be 0, it could be 1, 5, 7, whatever, but it is known, not unknown. Now, if that is the case, what to do on this system? Let me rewrite the equations that we have taken as an example, because this, again, the approach is the same. You have to remove now the second degree of freedom column, associated column, and the row. But how you do it, this is slightly different from how you we have eliminated a degree of freedom where we don't know its value. So let's consider this. Now, in this case, obviously the goal will be to remove this and to remove this, just like we have seen earlier. But do we need to write this equation now? There we wrote this equation because we wanted to have this in our file so that at the stage of back substitution, we had this equation to calculate a certain boundary condition, but a certain degree of freedom. But here the degree of freedom is a specified one. We know the value already, so there's no point writing this equation and storing it in your hard disk. You already know the degree of freedom here, which is 2. That is why it is a2, that is why it is called a boundary condition. But here you have to write the equation anyway for a different purpose. Let me explain. K21 u1 plus k22 u2 plus k24 prime u4 plus whatever that follows is equal to f2. This is equation number 2. Now we don't need to store it for calculation of u2, which is already known. But how is u2 achieved? That is, why is there a specific value for u2, that is a2. This a2 is imposed on this u2 because of a reaction force here. Some reaction force causes this certain amount of u2 to be maintained. So in this case you don't need this equation stored for the purpose of calculation of the value of this degree of freedom, which is already known, but for the purpose of value of this reaction force, which sometimes is needed. So now you rewrite this in terms of R2 is equal to K21 prime U1 plus K22 prime U2 plus K24 prime U4 plus whatever the values are. There could be other values here, minus. You have to write this down now in your hard disk. Written to the hard disk. So now at this stage, even if you eliminate this row, no information is lost because you have the necessary information already written down. But the other problem is still the same. You have these values k12 prime, k42, and there are maybe other values here also. All these get to be multiplied with u2, which you know has the value a2 here, which is known. So again, before eliminating this column, because we can only eliminate this row when we eliminate this column also, because this column, all these values get multiplied with u2. If u2 is not there, there's no point of these values. So we can only do that if these values are 0, just like in the last example. But here you don't need a row operation for doing that, because these values obviously are known, and this u2 is also known. Whether it's 0 or non-zero, it doesn't matter. Its value is a2, which is a constant. So all we need to do to make these 0 is simply take the product of k12 prime and u2, which is actually here a2, and take it to the other side, change the sign. This becomes 0. This one will become 0 by again, because this value is known, we don't need row operations to make this 0. As a result of this, you will have this k11 prime 0 0, k21 prime, k22 prime, k24 prime 0 0, k4 is prime. u1 u2 u4 f1 prime minus k1 prime, f2 prime, f4 prime minus k42 prime, a2, and so on. And here also all will be zeros here. Okay, so now at this stage, now you can just remove this, because this information is already here. You can remove this because these are all zeros, so you get this 0 0 u1 u4 and so, and obviously you'll have other values here, but again this one row and one column have been eliminated. And so on. And then obviously you'll have more elements added. But in both cases, whether it's a specified boundary condition on a certain degree of freedom that is occurring for the last time, or whether it's a simple degree of freedom which is unspecified, you want to calculate that, but it occurs for the last time. In either case, you do some operations as I have explained, and then you eliminate the row and the column. So the net result is, if this is the zero line and the total system n into n system is like this, if this is the number that you would have in your working memory if you were using the standard approach, not the wavefront approach, then in wavefront what will happen is something like this. You will have a certain value, element 1 let's say, then you add element 2, but then you add element 3, then somewhat reduces, you eliminate something, then you add, then it reduces, then you add, then it reduces, then you add. But then at a certain time what happens is, because you are reaching the end of the problem, so more and more degrees of freedom will get eliminated. It will increase, but then it will start decreasing also. At this point, at the very end, you will have only 1 degree of freedom in your working memory. At each stage you are writing equations. At each stage you are writing, whether it's a specified boundary condition or not, you are writing equations. In some cases for u, in some cases for r. And when you reach this point, last degree of freedom, you calculate its value, and then using all these equations you keep on back substituting and finding the values of all the degrees of freedom, unknown degrees of freedom, and any reaction forces that you require. So this is the procedure for Wavefront method. It gives a lot of relief to your working memory, and instead it uses your hard drive to store all these equations. Now I'll have just a few words on the node and element numbering when we use the Wavefront approach. This aspect is slightly different from your ordinary approach. I have just explained the algorithm, but I have not said anything about how to number your nodes and elements when you're using the Wavefront approach. Let's do it here. Let's take a simple 2D problem. Cantilever beam. Let's number the elements like this: 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. These are the elements. As far as node numbers are concerned, let's number them: 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 29, 30, 31, 32. This is a 2D analysis. Now, obviously, this is node number 1, this is node number 2. For 2D, node number 1 is associated with 2 degrees of freedom, u and v. So actually the degrees of freedom are 64 in this system. But I'll just talk about nodes here. Let's say degrees of freedom associated with element 1. Let's see from our connectivity. Element 1, you'll have nodes. These are nodes. Degree of freedom associated with nodes. So when I write 1, 2, 5 and 6, 1, 2, 5 and 6, then degrees of freedom are actually twice these. So I'm not talking about degrees of freedom, I'm just talking about nodes here. So when we have in our system degree of freedom number 1, element number 1, then you have 1, 2, 5, 6. These are the nodes which are associated with element number 1. Now in your working memory, for the moment you have this, but the moment you have this, you realize that node 1, this is not going to occur again. The moment we move to element 2, then node 1 is history, that's it, never to come again. So we can just remove, even at this stage you can remove node 1, and in your working memory you only have 2, 5, 6 node numbers, 2, 5, 6. Okay, now we move to element number 2. Now 2, 5, 6, 2, 5, 6, these are obviously still in the working memory. You have not been able to eliminate them yet, but element 2 brings the nodes 3 and 7 also into the system. But the moment you are finished with element number 2, you realize that now node 2 is also history. It's not, the moment we go on to element 3, 4, 5, there is no reference to node 2 now. So node 2 again goes. So we have in the working memory 5, 6, 3, 7 only. So even when you reach element number 3, you have eliminated 2 already. Now we reach element number 3. For element number 3, 5, 6, 3, 7, these are still in the working memory. They have to be. 5, 6, 3, 7 are already there. But for element 3, you have 4 and 8 also added, because they are part of element 3. And here you realize that node 4 is now irrelevant, because in element 4 onwards there is no reference to 4. Remove it. Others are still alive. 5, 6, 3. This 3 also goes at this stage. When you reach element number 3, not only 4 but 3 also goes. So in your working memory you have 5, 6, 7 and 8. Again 4 only, because you have now eliminated 4 already. Now you move to element number 4. This is 5, 6, 7, 8 still alive. And for element 4 you have 9 and 10 added. But here 5 becomes irrelevant, because here 5 has occurred for the last time here. 6, 7, 8, 9, 10 are those which you still have to carry in your working memory. You move on to element number 5, 6, 7, 8, 9, 10 are already there, and for element 5 you have 11 again added. At this point 6 becomes irrelevant. So 7, 8, 9, 10, 11 and so on. So new numbers are coming, old ones are vanishing. So this is under control. This is not increasing. If it was the ordinary approach, your live node value, so to speak, they would have increased steadily till a maximum value was reached at the end. Here what happens is there are only 32 nodes in the system. So here you start with 3, then 4, 4, then 5, then 5, steadily increasing, decreasing, increasing. But recall that at the end you will just have this one. Only 32nd node will be there, because by necessity all these will be eliminated one by one. and when you reach this situation here, very quickly elimination will take place. So something like this happens, and then reduce to only just 1 degree of freedom. One node actually, each node is actually 2 degrees of freedom. So this obviously will be followed by calculation of this degree of freedom for this, and then back substitution, because when you reduce all these, when you eliminate these, you write equations. Now we have numbered our elements in this shorter direction 1 2 3 4 5 6 7 8 9. Now had we numbered our elements in the longer direction 1 2 3 4 5 6 7 8 9 10 11 12 13, it could have been done. Had we done that, this at any time the number of nodes in the system, or what is also called the wavefront, this is called the wavefront, the number of nodes in the system or degrees of freedom in the system at any one point is called the wavefront. Number of degrees of freedom. Here the difference between degrees of freedom and the nodes is obviously 2 to 1. Each node has 2 degrees of freedom, so it's the same thing we are talking about. Number of degrees of freedom in the working memory at any one point. The wavefront takes a certain value, increases, decreases, increases, decreases, but after a certain time it starts decreasing, and then it reduces to 1. Now had we numbered this in the longer direction, then this 1 would have been eliminated the moment we had gone to element 2. Element 2 would have been here, but look how quickly degree of freedom 2 also got eliminated in this numbering scheme. The moment you reached third element, 2 was irrelevant. But if we had gone the longer route 1 2 3 4, then node 1 would have been eliminated, but for node 2 to be eliminated, it would have been necessary for us to wait till we went all the way here, and when we reached this point, then we would have been able to eliminate node 2. So which would have meant that the wavefront, the number of degrees of freedom held in your matrix, would have been much larger here. Ultimately it still would have reached the last degree of freedom 1, but in the meanwhile your working memory would have been obliged to store more information at any one given time. So it is always better, the moral of the story is, because when you are talking about solution by wavefront method, then your meshing becomes important too, because one part of meshing is node and element numbering. So if you are going to solve your FEM equations by wavefront approach, then you should make sure that you number your elements in the shorter direction. This makes your wavefront smaller, which you require, which you would like to have a smaller wavefront. If you number your elements in the longer direction, then your wavefront will be larger, which is not advisable. Now what about the node numbering? This is your element numbering. What about node numbering? Does it matter if this node was numbered, for example, if it was numbered not 2 but some other number? For example, if we had numbered in the longer direction 1 2 3 4 5 6 7 8 9, let's call it 9. If it was 9, does it matter? Doesn't matter here, as long as you had numbered your elements in the shorter direction. Then instead of 2 getting eliminated here, 9 would have gotten eliminated. So the total number of degrees of freedom or nodes in your system would have been same irrespective of the numbering scheme of the node. So for this wavefront approach, elements must be numbered in the shorter direction, whereas node numbers don't matter one way or the other. This is very different from your ordinary approach. In your ordinary approach, you are concerned with the bandwidth of the problem, and the bandwidth depends on the node numbers, not element numbers. There the element numbers are irrelevant. Here element numbers make all the difference, node numbers are irrelevant. So if you are concerned about your bandwidth, that is, you are doing it in the ordinary way, then you should make sure that your node numbers are node numbers are in the shorter direction. Nodes are numbered in the shorter direction first, and then covering the longer direction, and element numbers there don't matter. Here it's the reverse. Elements must be numbered in the shorter direction and then spanning the longer direction in this way, and node numbers don't matter. So that's all about this wavefront approach. In the next lecture we'll take up an example to demonstrate all this theory. Thank you.